is Professor Robert Boyer from Drexel University, who will speak about polynomial versions of integer partitions and their zeros. As usual, we're going to take the out-of-town speaker for dinner at Evelyn's restaurant at 6:45. If you'd like to join us, please let me know immediately after the talk. Thank you.
Great. Thank you, Doran. Right. So thank you for the invitation to speak today, Doran. Now, what I'm going to talk about today is based on a research program going back several years with two colleagues. One, William Bill Go. He's a retired professor from Drexel, and past 2 years or so worked with my PhD student Dan Perry, who's in the back row. So this is Dan. Right. So what I'm going to highlight are three polynomial families involved with partitions. So I'll talk more exactly what they are, what I call partition polynomials, plain partition polynomials, and odd partition polynomials, just to say I have three major examples. So here, exactly what they are. So by partition polynomial, so P of n will be the full counting of partitions of n, and by piece of k of n, I mean the partitions of n with exactly k apart. So that would be the number of terms of writing n.
Oh, so it's exactly, not as more.
Exactly, not less than or equal. Exactly, so it's exactly. So for instance, for F4, so it would be the number, so ultimately it would be the number of partitions of 4. So to write 4 with one term, there's only one way of doing it. With 2 terms, I guess there's 2 ways of doing it. And 3 terms, there's only 1, and 4 terms, only 1. So we have this polynomial.
We have up there, I think isn't exactly correct. The term weighted partitions comes to the polynomial itself.
Well, it doesn't matter for this purpose. Okay, so for a plain partition polynomial, first of all, by plain partition, I mean, again, ways of writing n as a sum of non-positive integers. So it'll be an array in which you sum up all the integers in the array, and that would give us n. And along any row or column, the integers would be decreasing. I'll talk about the trace. The trace would be some of the diagonal entries. So let me just look at a specific example of this. That's a notation, so let me go to the next slide. So for the partitions of 4, so of course you have an array with just one entry. For an array with 2 entries, either you have a single row or a single column. As I said, they have to be decreasing. So the trace is some of the diagonal entries. If you're saying one entry, it's the entry itself. In this case, you just have one diagonal entry. For trace 2, we see we have, what, 1, 2, 3, 4, 5, 6. And again, I guess the only time that we get more than one entry is for the trace. This is the last example. And for trace 1, we have all entries 1, and you just do a straightforward count. All right, and for odd partition polynomials, okay, sorry. Right. So for plain partitions and to build a polynomial out of it, I look at plain partitions of the integer n and its specified trace, and they would form the coefficients of the polynomial. So from what I just showed, then the degree 4 plain partition polynomial would have these coefficients. Okay. So for what I call an odd partition polynomial is just partitions in which all the parts, the summands, are all odd integers. Okay. All right, so I'm interested looking at the zeros of these polynomials. So let me just see what's there. So that's really the motivation of this, of looking at these polynomials. So I'll just look at the polynomials to the zeros of degree 1,000. So we see we get a very large family basically around the unit circle, and I will indicate why that's the case. And then there's a very sparse family of zeros which lie inside the unit circle. So we'll be able to actually, I'll give the actual equations for these. As the degrees run off to infinity, these zeros actually approach specific curves inside the unit disk, and I'll give precise equations for these curves.
So these are the zeros that happen to be in the unit disk. So there
Right.
are, because there are thousands of them, but most of them
Most of them,
are outside.
so these here, yeah, most of them are outside. There's only this sparse
So you're
family in the one.
focusing
Right.
So how many are there in this case?
Orders for
Oh, actually, I have a paper from about 4 or 5 years ago. I have counts of them. Right.
You don't
So I have
know.
heuristic formulas for predicting how many. So there are actually 3 curves, and I have some heuristic to tell you how
By
many.
looking at it, like 10? How many here?
What?
Can you just say how many in this case?
No, I didn't do a count. It doesn't seem like if you just, I mean, the polynomials
Yeah, but
have
just
real coefficients, so they're symmetric about the real axis. So there's only, I mean, you can see there's only about, what, 15 or less.
Yeah, 26.
Well,
26.
yep, 26, okay. And here for the plane partition polynomial degree 1,000, again, you see you get a family of zeros about the unit circle. We have a family along the bit of a negative axis, and this looks like perhaps a straight line, but it isn't, because these curves are very small, so unless it has enormous curvature, they'll look straight. And then for the odd partition polynomial degree 1,000, it looks like maybe you get the unit circle and maybe just zeros on the imaginary axis, but that turns out to be, actually, maybe there's this funny bit way near the number I, and in fact there is a very non-trivial curve there. You'd have to go to a higher degree polynomial to see this. Okay. So just so I can, in terms of a mathematics talk, do something, indicate something I could prove with some detail, let me go through an argument to some of the arguments show that there are zeros which do accumulate about the unit circle. Okay. So, and the proof uses fairly general techniques. All right.
You mean all the zeros?
No, not all the zeros. No.
Or some of them?
Some of them, yeah. I mean, you can see by the examples,
Yeah.
there's big family that goes around the unit circle, and then you have these more
Also a
sparse
subset
families.
of them?
Yes,
Yeah.
a subset will go to the unit circle.
So
Now,
1,000 is typical already?
yes,
Yeah.
right. But it's not typical of this internal structure inside the unit circle. Yeah. So for this argument, I'll remind everyone of this theorem of Erdos and Turan from the early 1950s. That has to do with the distribution, ultimately the distribution of the arguments of zeros in the complex plane of a polynomial. So for this, you need the constant term to be non-zero for this bound. And so the number of zeros in the complex plane, where the arguments lie between theta 1 and theta 2, look at that count. So this is of course, this difference here is normalized, multiplied by the degree, the normalized arc on the corresponding unit circle, that this difference is bounded by this quantity. So notice that inside the log, underneath the square root, we just have the sum of the magnitude of the coefficients. All right? Okay. Now to apply that result, in my case, I'm going to let n go off to infinity. So I just remember, I'm only going to talk about the argument for the what I call the partition polynomials themselves. So I just need the this well-known asymptotic for the partition numbers. Basically, it's this initial factor, and the main contribution comes from this exponential, which is order the square root of n, where n is the degree. And there are similar formulas for the odd partition numbers and the plain partition numbers. Okay, so to apply the theorem, you just do something very simple. You just divide out by an x, whereas the partition polynomials themselves, they don't have a constant term. So when I do that, I get polynomial degree n minus 1. So I just shift things, and as I indicated before, I need the sum of the coefficients, so that's just the partition number, and that grows according to this exponential law. Now what I'll be looking at is a normalized count of the zeros. So I just take the count of the zeros that lie in this angular sector, and just normalize by the degree. Okay? And applying the theorem for Erdos-Turan, I have this bound then between the count of the zeros that lie in this sector against normalized arc length. So that's bounded by ultimately the square root of the log of the partition number divided by this the root of n minus 1, the degree. Okay. So then by the asymptotic, this quantity grows like the square root of the log of this quantity, so then you just do the algebra. So ultimately you're left with a double square root on n divided by the square root of n. Of course, that goes off to zeros and runs off to infinity. All right, so what I conclude from this argument then is that the zeros are the partition polynomials, and the arguments are uniformly distributed about the unit circle. All right. And of course, because I have the asymptotics for the other two cases, the same result would hold. Yes?
All right, so it goes to 0.
Yeah, it goes to 0. Yeah, so it's an iterated square root. Yeah. Okay. Now, so I'm looking at an average count. So there's you can also use elementary arguments to show that to try to do an average count inside the circle or outside the circle, that the average counts go to 0. So what one concludes is that the zeros are uniformly distributed about the unit circle. All right. So in terms of normalizing the count of the zeros by the degree. So notice then that would, in a certain sense, the interesting structure is not the unit circle, but rather these parts families that lie inside. So this elementary argument then just washes away the structure I'm interested in. But you can't say something using very general methods. Okay. All right, so that's why I say, so we ignore the contribution of zeros inside the disk. So, so I introduce this idea of what, with Bill Go, this concept of zero detractor. So informally, this would simply be just take the collection of all the limits of zeros of the collection of polynomials. One can, and the examples that I'm interested in, you can say something more precise. So if you look at the zero sets as being compact, they're finite sets, so they're compact subsets of the complex plane. So you can look at those zeros as being the space of compact subsets of the complex plane. You actually can show that these finite sets do converge to a set in the complex plane under the Hausdorff metric. So that's exactly what the zero attractor is. All right, so we know what we're computing. All right, so to compute the zero attractor is great interplay with the structure of the asymptotics of the polynomials. So let me just indicate to you what the asymptotics look like in general. Then I'll go through the 3 examples in more detail and map it into the structure I'm indicating here. And then if I have time, I'll indicate how I would get these asymptotics using the classical circle method. Okay, so as I said, we're going to assume we'll assume that the asymptotics of these polynomials have the following structure. So we're just interested in the asymptotics inside the unit disk. And I'll assume that the unit disk is almost a finite union of open regions. So by almost, I mean that unit disk, so these regions fill up the unit disk up to the boundaries of these domains, okay? Right, so if you have the upper half circle and the lower half circle, then, you know, the real axis is missing. So that's what I mean by almost. Okay. So we assume that in these regions that the asymptotics of the polynomials have this form. So some function times an exponential. So for the partition polynomials, into the 1/2 times a specific analytic function L1. For another region, specific, you know, basically exponential into the 1/2, another analytic function L2, and so on. All right, so it makes sense that you would have n to the 1/2 because the partition numbers themselves have the asymptotics of e to the magnitude 1/2. Okay. Go. And we'll assume that these functions are non-zero. All right, now the regions themselves come from looking at the functions that describe the asymptotics, L1 and L2 and so on. So region 1 would be where the real part of the first function, L1, dominates the other L2s, L3s, and so on. The region R2 is where the real part of L2 dominates the other functions in the, giving us the asymptotics. All right, so as I go through the examples, it will map exactly into what I'm saying here. All right, and of course, if I have two adjacent regions, then the way I define the regions, their boundary then is a subset of the level set where the real parts are equal, right? And that's how I will get a specific description of the curve, is by saying real parts of these two analytic functions equal to each other. All right. Now, if one goes through a simple argument that involves taking roots, one can show that the zeros of the polynomials can't converge to points interior to these regions, R1, R2, and so on. So they're forced to lie on the boundaries. And with further results, one can show that every point in the boundary is a zero, limit of zeros. So I call the zero detractor just given by, I guess this, I'm trying to be simple. Sometimes being simple is not quite okay. I guess this is okay. Yes, it's boundary of the regions. I think that's okay. Yeah. All right. Right, so the boundary of the regions is okay. Boundaries are a subset of the level sets. Yeah. So I'll have three examples. I'll give you, that's what, next thing I'll do is examples of this. All right, so. All right. All right, so what I need to do then is have polynomial analogs of the asymptotics to find the zero detractor. And once I have that, then the zeros will converge to the boundaries of the regions where the asymptotics change. Region 1, they're basically ruled by function L1. Region 2, they're dominated by L2, and so on. All right. So I'll just go through the list of my families. I'll look at zeros and describe the asymptotics. All right, so I'll go through these examples, and then I'll indicate how one would prove this. All right, so I have my three examples: the partition polynomials, the plain partition polynomials, and the odd partition polynomials. All right, so that's what I had originally, degree 1000. And this is what the zero detractor turns out to be. All right, so I have these inside the unit disk. I have it's symmetric about the real axis. So I have these three curves. So I have this one family that's quite large, this green curve, and a small red curve. So when I originally plotted these, I used these colors, and after so many years, I just always think of them in terms of this color scheme. Okay.
Almost a Valentine.
Excuse me?
Almost a Valentine.
Yeah, another talk I had a set of polynomials that looked like the Batman movie was very popular. I had something that came out that looked somewhat like a cape and a little hat. Excuse me?
It looks like Pac-Man.
Pac-Man, okay. Right. So I just have just the upper half plane. All right. So then I have a close-up of this. So when I indicate put some more zeros in there, it's nice to have it close up. So this curve is very, very small. So, right. So then, I mean, as I say, this is a really sparse, the number of zeros that lie inside the unit is just very sparse. So, I mean, usually if you have like 1,000 zeros, you think, oh, you get everything filled up. So, well, I have an old machine, I never could get beyond 70,000. So for 70,000, polynomial degree 70,000, plotting the zeros here, I mean, you see that you only get one solitary zero that lies on this curve, and you know, you see that they're still very discrete the way they're distributed. All right, so I do have results about the densities, but no, for the purposes of talking 48 minutes, I'm going to talk about density results. Okay. Right, so then I decide, well, I'll fill it up. So I do have these other intermediate zeros, 25, 30, 40, 50, 60, 70,000. So as I said, that adds up to, I think, 275,000. Just talking before the talk, and you see, you still get some, even with all those potential, I mean, nearly 300,000 points, you still don't get that much there, right? You still see some, you know, empty gaps, right? So you're converging very slowly, obviously, to these curves. Okay, so let me write down the functions. I had my fun, so it's fun to get them, but no, the more satisfying pleasure is actually having the proofs. So just to write down the formulas for the asymptotics, we need the classical dilogarithm function. So if we just have x over n, then that would give you what, minus the log 1 minus x. So maybe that's why they're called there's a dilogarithm. And now the functions that come into play to describe the asymptotics are given in terms of the dilogarithm. So we have a family that involves the square root of the dilogarithm, so 1 over k, the square root of the dilogarithm of x to the k. So that's what the family looks like. And so we have then, we can show that there are three regions in the unit disk. So that makes sense. Maybe I should go back. So I mean, I've been looking at this for many years. So there's 3 regions. So let me go back to it. Right. So we have this region, which is bounded by the red curve and the green curve. So that would be region 1. There's region 2, bounded by a little bit of blue and the red curve, and there's region 3, these 2 little slivers. Okay? So the sense of the asymptotics of the polynomials depend on different regions inside the unit disk. Okay. Right, so in the first region, family of polynomials, major contribution to the asymptotics come obviously from the exponential factor, so twice the square root of L1 of x. All right, so if you think back in the formula for the partition numbers themselves, if you look at the dilogarithm, that's you know, summing up x to the m divided by m squared. So you put in 1, you get pi squared over 6, and formally if you put that in the formula, then we'll get back to the number in the exponential for the partition numbers themselves, which would be e to the pi square root of 200 over 3. Okay, so and then we have these, so this would give rise to what I called, in the general scheme, A, little function, little a, and so we have similar asymptotics in the other two regions. Okay, and as I said, just to make
So when x equals 1, can you rigorously get it? Only
No,
formally?
no.
And the asymptotics don't work on the
No, they don't work in
No,
these.
okay.
All right, so here we have, as I said, I think I'm color-coded. For this example, I'm very color-coded. So we have these three regions, and as I said, the first regions where the real part of L1 dominates the real parts of L2 and L3 and so on. So the curves then are described by these equations. You should just set the real part of L1 equal to the real part of L2 and so on. So it's described by portions of these level sets. The real part of an analytic function or harmonic function. So you're looking at different level sets of harmonic functions here. Okay. All right, and one can compute, numerically all the points. There's some of the curves do intersect in circles, so you can compute all these points very accurately.
So you don't have a description of these numbers in terms of pi or e? These
No,
numbers?
no, well, I mean, besides this
0.691.
equation, say
No, this
here.
0.69, the first one. You can only express them in terms of...
No, so they're close to like 2 pi over 3. It's close to like 120 degrees, 3 pi over 4 radians, things like that, but it's not
But not
quite.
exactly, yeah.
No, it's not exactly.
And you have no explicit formula. You
No,
have
I
no-
mean, it's just this. I mean, they solve this equation.
Oh,
So these
right.
numbers solve these
Implicitly.
equations.
Yeah.
Right.
The
right.
solution of this.
Right. So that's
Oh, yeah.
exactly that.
Is it possible here in terms of?
Now, in this case, for the dilogarithm, if you look at the dilogarithm of the unit circle, the real and imaginary parts do have closed forms, right? So the real part is a quadratic, and the imaginary part is a very explicit integral, so-called Clausen integral. So you can write down things very more precisely in terms of other special functions. But in general, you just are led to equations with that general structure. Okay. All right, so let me look at, so I'll go through the same type of description, this overview for the plane partition polynomials. So we have, I guess for sake of, I guess I had it, so I have degree 500 here. So not much changes. The structure is fairly, compared to the original partition polynomials, fairly straightforward in terms of the zeros populating the curves. So going to degree 2200, we see this family here, and this contribution along the negative axis. Of course, for the partition polynomials, it's very fortunate for the partition numbers in parts. They're easy recursions to get them. While with these plane partition polynomials, there aren't good recursions, so it's hard to get beyond say 3,000 or something to get the coefficients to look at polynomials. Okay. So here I indicated the zero tractor. So we have this, as I indicated repeatedly, we have this segment along the negative axis. Now, this looks straight, but as I said, it's just a small curve, and it's not really straight. Okay. So here I have lots of zeros and same tractor. All right, and here's a close-up. I went. Right, so I know it's not straight. We'll see that we have equations involving special functions to get these points of intersection, which I indicated by these blue diamonds. So we know it's not really straight. Okay. So the plane partition polynomials, we can have similar structure. Instead of having dilogarithm, we have so-called trilogarithm. So Dye logarithm, we just had m squared, here we have m cubed. We have similar family of functions to describing the asymptotics. Here we need the cube root rather than the square root. And the zero tractor then would be a subset of the level set